Hello everyone, hope you're having a good day. Today we'll be talking about benzene and aromaticity. So first let us talk about the common benzene derivatives. Okay, so I don't really have all of them here, but I have the most common ones. So the first one, and I suggest as we go along, you try to remember this on your own. The first one I have here is the toluene. We know that as that's a benzene with a substituent of methyl, one methyl. And then silane is benzene with two substituents of metal, but these metal groups have to be in a 1-2 proximity to each other. Okay, and then benzoaldehyde is a benzene with a benzene with a aldehyde group, and then aniline is a benzene with an amine group. Okay, benzoic acid is an benzene with a carboxylic acid group. Phenol is a benzene with a OH group. Okay, so now we're going to go into naming our benzene. So when you name benzene, the first thing you need to determine if it's monosubstituted, disubstituted, or multi-substituted. When meaning it has 3 substituents or more. Okay, so if it's monosubstituted, like for example toluene, right? You don't need to put a number like 1 toluene. It's just going to be toluene. But if it's disubstituted, you're going to need one of this. Okay, so depending on the substituents are, how proximal they are to each other, you're going to use one of this. If they're 1-2 proximity from each other, it will be ortho. Okay, if they're 1-3 proximity to each other, it will be methyl. If they're 1-4, meaning they are across from each other, it will be para. Okay, so let's go ahead and take a look at our first example here. So our first example here, we see that it is multi-substituted, meaning it has 3 substituents. It has this, this, and this, right? So we want to actually use number locations for this because it's multi-substituted. The first priority will go towards the substituent that's part of this common benzene derivatives. If you look at this example, we have a carboxylic acid. Okay, so this actually gives us a substituent of, remember, benzoic acid. So this will get a number 1, and then the next number 2 will go to the closest substituent, right? So that would be fluorine, and then you can just number in that direction. Okay, so the first thing you want to do is get down the name of your derivative. In this case, we have a 1-benzoic acid. Okay, and then I would suggest that off to the side you put the substituents. We have a 2-fluoro and then a 5-chloro. So with this, you want to remember when you do IUPAC naming, you do it in alphabetical order, the substituents in alphabetical order. So the chloro is going to go first because it's a C. Okay, so if we put this together, it will be 5-chloro, 2-fluoro, 1-benzoic acid. That's the name for that structure. Now let's look at this. What we notice here is that this has 2 substituents, right? So that means it's disubstituted. So what we need to know, what we need to use as a prefix is one of this, and that's gonna be determined by the proximity of the substituents. So say this is location 1, this would be location 4, right? They are across from each other, so that's para. So we know we know that the prefix we're going to use is para or P. Okay, so first of all, you need to determine what is going to be your derivative, right? Your derivative is right here, right? Is the aniline, right? Because you have an amine group. So remember, you don't need the number. So just first thing you should do is put aniline, okay? And then what is the name of your other substituent? This is a third butyl, okay? That's a third butyl because you have 4 carbon, 1, 2, 3, 4, right? Connected to the benzene, and the carbon that's directly connected to the benzene is tertiary, okay? So that's a third butyl. So we're going to put butyl right next to that aniline. Okay, so, and then remember our prefix is para, so you can put para or P. So I'll put P, standing for para. So that will be para third butyl aniline. That is the name of this structure. Okay, so now let's go into how to determine aromaticity. There are 3 different terms that would describe aromaticity. There is non-aromatic, there is aromatic, and there is anti-aromatic. Okay, so these are the criteria to determine if something is to determine something's aromaticity. Okay, so let's discuss that first. If something is cyclic, if it's fully conjugated, and it's planar, so if it meets these first 3 criteria but it doesn't meet this criteria, you have to check this criteria. I think this works best if we do an example. Okay, so the what do these 2 mean down here? These are how this is when you count your pi electrons, right? And how do we count our pi electrons? When you have a positive charge, that will count as 0 pi electrons. When you have a radical, that will count as 1. When you have a negative charge or a pi bond or 2 or just a lone pair, that will count as 2 pi electrons, right? So let's take a look at our first structure, and as we go on, we'll discuss more as needed. So our first structure, okay, we need to look at the criteria here. We see that it is cyclic. The question is it fully conjugated? So it has this carbon, and this carbon, right? These 2 carbons are conjugated because they have a pi bond connecting them. And then this carbon up here is also conjugated because it has that negative charge. Okay, so it's fully conjugated. Okay, is it planar? Yes, it is. It's planar. So the next question is, does it have 4n plus 2 pi electrons, meaning it follows the Huckle's law? And it's if it has a 4n plus 2, then it would be aromatic. Or does it have 4n pi electron, meaning if it's gonna be under Breslow's law, meaning it's gonna be anti-aromatic. So based on what we've learned on how to count our pi electrons, let's see. So we see that it has a pi bond there, counting as 2 pi electrons. It has a negative charge, counting also as 2 pi electrons. So if you add these 2 together, that will give you 4 pi electrons. Okay, so we need to determine if that will be 4n plus 2 or 4n. So n, in this case, when we're talking about 4n plus or 4n, n is an integer, right? N is an integer. An integer can be anything from 0 to infinity. Okay? So if we put 0 in this for n for over here, that will give us 2 pi electrons, right? If we go up in number and we put 1 for n instead, this will give us 6, right? 4 times 2 plus 2. Oh, sorry, 4 times 1 plus 2 is what I meant to say. That will give us 6, right? So this doesn't have 2 pi electrons, neither does it have 6. So we know it doesn't fit that criteria. Let's see if it fits under 4n. So for n, if we put 0 for n, that wouldn't make sense because that would just mean 0 pi electrons. That means it wouldn't have been conjugated to start with. But if we put 1 for n, if n equals 1, and for this, that would mean that we have 4. And in this case, we do have 4 pi electrons, right? So because of this does follow Breslow's law. And it's going to be anti-aromatic. Okay? It's anti-aromatic. So let's look at the next structure. So whenever you come across a structure that has heteroatoms that have lone pairs, you want to go ahead and draw those in to start. Okay? So we know oxygen has 2 lone pairs. So let's see, is this structure cyclic? It is. Is it fully conjugated? Let's see. So we have a carbon here, a carbon here, a carbon here, a carbon here. Okay, so these 2 carbons are conjugated. They have a pi bond connecting them. Okay, but this and this carbon, they are not conjugated because they have neither a charge, a lone pair, or pi bond. So this is not fully conjugated. It's already disqualified, and thus it's non-aromatic. So something will be non-aromatic if it doesn't meet the first 3 criteria. Okay, so we'll take this is non-aromatic. Okay, let's see the third case. In this third compound, we have nitrogen. Okay, nitrogen has a lone pair, and also nitrogen is a heteroatom. Okay, just like oxygen. An heteroatom is an atom other than carbon. Okay. Okay, so since nitrogen is a heteroatom, there's another rule that we'll discuss as we go on. Okay, so first let's determine, is this structure cyclic? Yes, it is. Is it fully conjugated? Let's see that. There's a carbon here, there's a carbon here, there's a carbon here, and there's a carbon here. These 4 carbons are conjugated because they have pi bonds, right? So, and this nitrogen is conjugated. It has a lone pair. Okay. The question is, will this nitrogen be able to donate its electrons into the structure? Okay. Would that lone pair be able to participate in conjugation, basically? So we'll answer this more as we go through counting the pi electrons. Is it planar? Yes, it is. Okay. So now the question is, does it have a 4n plus 2 pi electron or 4n pi electrons? So let's count up what we have already. Okay. We know that this pi bond counts as 2 pi electrons. We all know that this pi bond also counts as 2. Okay. So without looking at the heteroatom right now, we have 4 pi electrons. Okay, that would not be good because 4 pi electron means it's following 4n, right? Meaning it's going to be anti-aromatic and be unstable. So we need to see if nitrogen were to donate its electrons into this structure, would it become aromatic or not? So like we said before, lone pairs also count as 2. So if we add 2 to 4, what do we get? We get 6 pi electrons. And we know that if we set 4n plus 2 to 6, right? We do get an n equals 1, right? So that means this follows the 4n plus 2 rule. Okay? Since the 6 pi electrons follow the 4n plus 2, and we only get this if nitrogen donates its electrons, then we'll actually go with that and say that this structure is aromatic. So from that, you should keep in mind that an hetero atom will only donate its electrons if it helps the structure be aromatic. But if it doesn't help the structure be aromatic, it wouldn't donate its electrons. So that will be it for this video. If you have any other questions or comments, please let me know. Thank you so much for watching. Please don't forget to subscribe, like, share, and comment. Again, thank you for watching, and I hope you have a wonderful day.